Hi, fellow geochemists and geochemistry enthusiasts. Welcome to GeoChemISTea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire future geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Scher, and this month we're talking with Hugh De Souza about the past, present, and future of analyzing gold. Hugh De Souza worked at SGS for over 27 years, ending his career as the Director of Mineral Technical Services, and before that at the Ontario Geological Survey, amongst other positions. Hugh, can you tell us about your time in the minerals industry and your road to get there?
The first part of my career was mainly academic. I embarked on a PhD in geochronology. I studied geochemistry at Edinburgh University. I was working at a research reactor center where they had all the mass spectrometry equipment. So this was in East Kilbride. And while I was working in the Carboniferous volcanics of central Scotland, so I was right in the middle of the field areas. I could go out at weekends and collect rocks. I processed them. So I crushed a lot of rocks. I separated a lot of minerals, did a lot of chemistry. I learned everything about labs in that period. My intention would have at that time was to go work as a field geologist, but I never got the chance. And I ended up in the lab. So that was how I got introduced to analytical geochemistry. East Kilbride was followed by University of Geneva, working in ophiolites in the Middle East. But the main task there was to try and set up a lab for rubidium strontium at the time. But didn't work out too well because our mass spectrometer was really bad. I learned a lot about fixing equipment. And at that stage, I decided that I didn't want to continue in sort of academic life. And Canada seemed like a place where there was a lot of geology. So I went there and arrived in one of the biggest downturns in the industry. I managed to get a job at the University of New Brunswick. I was working on scanning electron microscopy, even though I didn't know anything about it, but I figured it out. And really, that got me started on the mineralogy, use of automated equipment for mineral identification. So the precursors to what became QuemScan and MLAs and so on. And we were working on process mineralogy, looking at the ores from northern New Brunswick, looking at silver. And I guess that was my real introduction to the industry. After UNB, I went to Ontario Geological Survey as a mineralogist, although in our section, we had a fire assay. And I ended up as supervising that fire assay. And that was my introduction to the fire assay method. So at that time, any prospector would get free assays, maybe 10 free assays, and we would do the assaying for them. It was a really interesting position because I got to see a lot of rocks and minerals. And then by accident, I became the head of the unit. It wasn't my intention to go into management. We moved up to Sudbury and there was a lot of change in personnel and I ended up being manager of that unit. And there was a lot of analytical equipment that we were purchasing for a brand new lab in Sudbury. I delved deeply into the analytical geochemistry side. Shortly after that, SGS recruited me and I became manager of their geochemistry in Canada, based in Toronto. That was a lab called X-ray Assay Lab, which is quite an interesting name when you consider it in the context of what Chrysos is doing these days. But for 10 years, I managed their analytical geochemistry lab. There was a number of fire assay labs that we had in our operation, new ones that we put, for example, in Red Lake. And so I got a fair amount of experience in that area. About the time, I think that the 2000s, we purchased Lakefield, SGS purchased Lakefield, and then I joined the mineralogy side of it. And I don't know, very quickly became manager of the Diamond Group, which is really a lot of fun, very different from what I was doing previously. But I had done everything in that area in my PhD, which was looking at rocks that were very much like kimberlites and all the mineral processing and mineral separation, et cetera, I was already had a lot of experience in it. So there about 4 or 5 years until the business collapsed in the financial crisis, and then transitioned to the area of geometallurgy, where there was both mineralogy, geochemistry, working alongside metallurgists, and got to learn about a whole different side of the business, the processing part of it, the important part of it, extracting metals from rocks, essentially, and using a variety of analytical techniques to characterize your rocks. So that became part of geometallurgical characterization. In the last few years of my time with SGS, because of all my experience, I was out there talking a lot to clients about analytical problems, mineralogical problems, and also trying to introduce new techniques, trying to get SGS interested in the core scanning methods, which were just starting out early 2010, 2012. So we worked initially with core scan on hyperspectral scanning, and then mineralized with XRF scanning. And it was a real good introduction to this emerging technology, which has blossomed considerably since that time. In fact, since I left SGS, there's a lot more techniques available, and it helps a lot in logging core properly and characterizing it so that if you're in a mining situation, you know what to mine much more easily, and saves a heck of a lot of time. So that's essentially my journey through the industry, but I specialized in a lot of areas, certainly in mineralogy and in geochemistry. And I think one of the advantages I had in geochemistry was, as a geochemist, as a mineralogist, I understood the rocks very well. And you have a saying, in mineralogy dictates the metallurgy, but it also dictates the analytical chemistry and how minerals react or don't react when you subject them to certain processes. And understanding that is really key to how you interpret your geochemical results. It's a bit of a twisted path, maybe not in the directions I wanted, but still ended up with a pretty good career and a lot of contacts within the industry. So I've carried on in that and trying to work with the local groups here in Toronto and trying to arrange talks and so on. So
Yeah,
that's
I
my
love it.
story, Sam.
It's a great story. Yeah. Like I said, there's probably only two people I've talked to that have ever had a linear path. And this one's really interesting. I think in the sense that you wanted to be a field geo, but you ended up as an analytical chemist.
It, yeah, and I had a good, I think, innate skill at it. I learned to do, when I was doing my PhD process, a lot of samples very quickly, do a lot of different types of analysis, and understanding the physics of instruments was also very helpful at that part of it. Maybe it was meant to be, and certainly my field skills have deteriorated a lot since that time.
No, that's amazing. Yeah, now you're our second analytical geochemist on the show. And again, it's just a field that I never really thought much of. Not that I didn't believe that people at BV and ALS and SGS and all the other ones that said that they were geochemists, I believed them. But just seeing from the other side and hearing about all the intricacies of instrumentation, having worked for a vendor where also I was working with instrumentation, having understand the physics of that instrument, you can really appreciate how it's a really interesting interplay of disciplines and how something that, yeah, it's not a career that many people think of, but it's definitely something that we need. So for anybody listening that's looking for a career, it's an interesting one. That's great. So I want to thank you for sharing that with us. But now it's tea time and we want to hear what you got to say. So let's go.
Okay, I put a talk together for a session I'd organized for AME a few years ago on coarse gold, and talked about the analytical part of it, because that's a very problematic area. It was at the time in 2022 when we did that talk. And the Chrysos photon assay was had just been introduced, and it seemed the answer to the issues we'd had with the standard fire assay procedure. And you need to understand the fire assay procedure has been around forever. In fact, it's over 4,000 years old. And it's amazing tribute to the early analytical chemists or whatever that they worked out this method, because lead was discovered maybe 3000 BC. By 2500 BC, there are references to a fire assay method using lead and concentration of gold, removal of the silicate matrix. We can see that in cuneiform tablets in Asia Minor, so in Troy and central Anatolia. There are indications that people were using this fire assay technique to measure gold and to purify gold. But the first real understanding of what this method was comes from a place called Sardis, and from the time of King Croesus. Now, King Croesus is a name that still resonates today it's synonymous with extreme wealth. He was probably the first kind of billionaire there. And it's an intriguing story because it was written up to some extent by Herodotus about 100, 150 years later. But what he did was he introduced bimetallic coinage, so pure gold, pure silver. And there's a tremendous monograph from the British Museum archaeological team who dug around in the waste dumps in Sardis, which is his capital, and have worked out the process that they used to measure gold. Because having the pure coins, you had to have a way of verifying that they were indeed pure gold or pure silver. And one of the amazing things in that monograph is when they go back and analyze these coins is the very even metal content of these coins. So it's always the pure gold coins are around 98% gold, the silver coins, 98% silver. They worked out a process called the cementation process, which allowed them to purify gold and purify silver and create this bimetallic coinage. And I think my conjecture is that people probably had a lot of gold dust in their houses, which they from panning in the streams in the area. And they exchanged this gold dust for his coins. And that brought about an explosion of business from which he became extremely rich. So we have evidence that he had a lot of gold dust, and he went around Greece talking to various oracles as to what would happen to his empire. And the oracle at Delphi said to him, a great empire would be destroyed if he went into war. And at that time, it was the Persians on the eastern edge of his empire. And he thought he would come out the winner. So he went to war with the Persians and promptly lost in that first battle. And he was captured, and his capital was occupied by the Persians. Now, normally they would put everybody to death, including King Croesus, but King Cyrus, the Persian king, kept him around, maybe because of his business acumen, and eventually ended up as being a tutor to his son. And it was from that time that the Persians actually introduced coinage. I believe that coinage and how you use it was his specialty and saved his life later on. So he was king of this Lydian Empire from about 560 BC to 547 when he was deposed, and about the time he died. But in that time, he accumulated a huge amount of wealth, and it's based on this development, the cementation process, which would have been introduced into the fire assay process. So from that work from the British Museum, we had a fairly good idea of what was happening in the fire assay process. You mix your sample with lead, you extract the gold, and then you have to find a way of separating the gold from the silver. And that's where you use the cementation process, which is mixing of salt sodium chloride with brick dust, and you create a chlorine vapor, which removes the silver, and you're left with the pure gold. So fast forward to the 1550s, by which time the various alchemists had worked out a number of methods to improve the fire assay process. And we have a book, De Re Metallica, written by Agricola, a German chemist, who describes in great detail the fire assay method at that time. And by then, they had discovered mineral acids like nitric acid, which they could use to separate the gold from the silver in the fire assay process, that process we call parting. And his description of the fire assay process from that time is very much like the fire assay process we're even using today. So if you look at fire assay books written in the early parts of the 1900s, they have the essence of the method that Agricola had. And the key thing, he said, it's a very complex method. If the assay is going to set about this, you shut the door, make sure you have no distractions, and focus on what you're doing. And that is very true to this day in the fire assay process. It is actually quite a complex process. Really, there are two parts to it. One part, we mix the sample with the flux because that is the process where we pre-concentrate these low levels of gold and bring them to a higher level so that we can measure them with the instruments we have. And the second part of it that causes a lot of difficulty is the nuggety nature of the gold. That is, gold occurring as particulates in the sample. And if you sample it if you take out a scoop of the sample, you might get a lot of nuggets in it and you might have a high value. But if you repeat it, you might get a lower value. So that's a problem we've always had within the fire assay process using samples of 30 or 50 grams that they're too small to properly sample. And therefore we get these fluctuating values, what we call nuggety values. There needs to be a process there that takes into account that corrects this nuggety nature of the gold. And the process is essentially a screen fire assay where we screen the sample at 150 mesh. We take the plus fraction where the gold nuggets are concentrated and assay that entire sample and a couple of samples of the minus fraction. And from there, we can calculate what the real value of gold in that sample is. So the samples can be 500 grams, 1,000 grams. From that, we essentially worked out you need to have pretty large samples to get a good assay. And essentially, the sample size we're using in the standard fire assay process is a real issue when you have particulate gold. For low-level gold, which is better distributed, it's not really a problem. That is the issue that has always plagued fire assay. So it's in that context I put the story together because when photon assay came on, it really addressed these two issues. We had a new physical process that measured gold using sort of gamma activation analysis and was able to do that on a large sample of 500 grams. So it really turned out to be an answer to the coarse gold problem that has always been an issue within the industry.
What do you guys do in the lab when you have separated out the gold during fire assay? Do you just throw it out or what do you do with it? Do you put it in your pockets? Like,
No. So what happens? You remove the silver, and so you have this tiny gold button, which you either
mm-hmm.
dissolve in acid and measure it on the instrument, or when you've got a lot of gold, you measure it on a balance, so for gravimetric gold, and you keep that gold bead. So you collect them over time.
Yeah.
If you've got a rich gold mine like we had in Red Lake, that can be quite a bit of gold over time. So they're all collected, and eventually the lab sells them off to a refiner, and then we have enough money for the Christmas party.
Well, there you go. That was my point. Okay.
Huh.
Oh my God. That's such a side hustle. I love it. It must have been great Christmas parties if you had a good year.
Oh yeah, it would be. And if you had a rich gold mine there, yeah, that would have been quite the party indeed.
Oh my God. That's how you guys always have those great PDAC parties too, I guess then. Just comes out of the gold find.
For a big organization like ALS or SGS, with lots of fire assay labs, they probably collect enough gold to treat their clients to a nice party at PDAC.
This is a side hustle. Wow.
Yeah.
This is the real tea.
Yes. That's with the fire assay focus. With the photon assay, you're not going to collect that gold because you don't do a pre-concentration step.
Mm.
I comment on the impact of this disruptive technology on our geochemistry business. That's going to be one of the unattended consequences, perhaps. We're not going to collect enough gold to have our party.
Things
Yeah.
people don't think of to start with. Yeah. Maybe if it's price inhibitive, maybe people still go with the fire assay. And then there you go. You got your Christmas parties.
I don't think at this stage that fire assay is going to disappear entirely because one of the issues that comes up with some of these new technologies, and I have to say, we're at a time where in the last 5 to 10 years, there's suddenly been an influx of new technologies like photon assay, detector, different ways of measuring gold that has given us a lot more options. Okay. And I've been involved with fire assay maybe 40 years now, and I've never seen a time like this where there are so many new techniques available that give us options of choosing other methods other than fire assay for our purposes. And one of the issues with fire assay I had mentioned is it's slow. It's a complex process. There are a lot of steps to it, and therefore it tends to be pretty slow. So it can take from start to finish probably a whole day or 2 days to carry out with the fire assay process. Whereas what we're seeing with these newer technologies is addressing that slow turnaround by a very fast analysis. So photon assay now is done within a couple of minutes, and 10 minutes from the time you introduce your sample to the time you get it out is very much faster, as is detector process. Also something that is portable, can be done in the field if you're doing a soil survey, and processes multiple samples. So you have your results by the end of the day. So these new methods have been addressing one of the big weaknesses of the fire assay process, which is it was slow, because what we saw in the early 2020s was turnaround times of 3-4 months, and that was causing the industry a lot of problems, in part because we'd been through a downturn and nobody was interested in investing in new fire assay labs. It takes a lot of money to put a fire assay lab together, one of the modern fire assay labs, and it takes a lot of time to train people to do the measurement properly and avoid all the QC problems that can occur with the multiple steps. So what Agricola said in sort of 1556, focus on the task, is still true today. If you're doing a fire assay analysis, you need a well-trained crew who just focus on what they're doing to make sure that there are no problems that come from, say, mixing up samples or contamination of samples, etc. So it is quite a complex process, as I said, and you need your technicians carrying out the work to be trained following the standard operating procedure. And that's why when you're selecting a lab to do that, make sure that they have this ISO 17025 certified method. It's the method itself that is certified. And as part of that certification process, the auditors will check on the training of your assayers that you can conform, that the method is fit for purpose, and also that you are analyzing enough reference materials to verify the data that you're producing. And that's you take part in round robins, like the one organized by CanMet, which all the labs partake. And that tells you whether or not the data you're producing is good and within a standard range. So that's an important part of the certification process. So in selecting a lab, that's a key certification to watch out for.
We'll get back to it really quickly, but I just wanted to ask really also very quick. So we've talked about in terms of sources of error, them being very manual, very human related. Are there any other sources of error for this process, or is that about it?
Essentially, these days, people are using multi-load furnaces where they can take 50 or 84 crucibles, but you can't mark the crucible with the sample number because it's heated to over 1,000 degrees. The samples are in crucibles that do not have any sample identification on them. So they have to use other methods, positioning the samples correctly, putting markers for the crucibles of a certain number so they know what sequence there is, because it's very easy when you're loading or unloading to mix up the samples and twist the whole lot around. And you might not notice then that you mixed up the samples, and the data then goes into the spreadsheet and you do not have the sample verified. In most of the other analytical procedures, we have test tube markers or barcodes that we can use, but the fire assay procedure, you can't use that. So that's certainly one of the issues. So it relies on a standard procedure where there's people who are really well trained to carry out these procedures, and using some of these markers to ensure that you don't mix up your samples. The other issues arise from contamination of the flux that you're using. So essentially the flux is there. It's a lead flux mixed in with something like sodium carbonate, sodium tetraborate, which is there to melt the rock sample. So you're melting the rock sample, liberating gold, which is then collected by the lead droplets. So that essentially is the fire, the concentration step. You're concentrating all the gold in the sample into this lead. And that then, because of its specific gravity, drops to the bottom of the crucible. In that process, the flux or the lead can be contaminated with gold. So that's certainly an issue. If you've been running high gold samples, it's possible that your furnace also gets contaminated. So you get tiny particles of gold that may drop into the crucible. And just remember, 1 ppb of gold and it's one atom in a massive room that you're trying to measure. That's a very small number. So at low levels of gold, it's quite easy to get contamination. That has always been an issue in fire assay labs. So you have to track your crucibles really well to make sure that these labs will reuse crucibles. Make sure you're not using something that's been used for high gold sample when you're doing a low gold sample. QA/QC processes are critical in fire assay procedures. Now, this new photon assay system seems a lot simpler to operate because it's about the size of 3 containers. Most of the action is happening behind the scenes. So the operator essentially is putting samples in, pressing a button, and there's an automated process for measuring the sample. And then the samples come out at the other end and the data goes off for the QC check. So it's, in terms of operation, it does not require the same degree of training and attention to detail as fire assay. And I think that is the reason people have been so interested in this new technology, in addition to the different way of measuring gold.
Why is it that we use lead buttons? What is so attractive to them for the gold that it just says, oh, let's separate?
So essentially, it's partition coefficients.
Mm.
Essentially, it's like in a magna, right? So the lead has a higher affinity for gold than the silicate matrix. So you have a melt, and you have these little droplets of lead
Mm.
in that melt, and what it's doing is it's scavenging the gold out of the silicate matrix. So essentially, and as a peak concentration step, it works tremendously well. And I'm just awed by the fact that people had discovered this and were using it 2500 BC. That's 4,000 years ago.
Yeah. Same. I'm like,
That they'd worked
this is
this
crazy.
out, and we're using it to measure gold. So it's probably very likely the oldest analytical method that's out there. All these QA/QC things that I described, they were aware of that. They had reference materials that they used to verify that the fire assay was done correctly. And a lot of what we use in our modern QA/QC procedures came from that time. When you read Agricola's book from 1556, he essentially says the same thing. You have to use these QC materials to check out your gold values. Now, I should say that fire assay was not the only method that they had. So in 550 BC, they had another method, which was called the touchstone method, which is essentially a streak. So if you have a coin, you produce a streak on a black rock, and they had some very good pebbles in the area. They had the right degree of roughness and were dark enough for you to see the streak. And then you compared it against standards of known composition. So it's essentially like you use a streak plate. So that was known as the touchstone method. It was very quick and enabled the person to figure out exactly how much gold there was in that sample. And then 400 years later, Archimedes left out of the bath and came out with this specific gravity method. And that was a third method that was used, measure the specific gravity of the sample to establish that it was gold. And these three methods, fire assay, touchstone, and the specific gravity method, are still used by mints today. So the Swiss mint or the British mint, English mint, and even the Canadian mint are still using some of these methods. Okay, so it's amazing longevity of these methods for gold. Certainly the streak method is quick and dirty, gives you roughly what the gold value is.
Yeah. But you lose them along the way.
Yeah.
Okay, we've talked a little bit about photon assay, but can you explain, because it makes it sound very chemistry-y with the photon in the name. Can you explain exactly what the tech is and what it's doing?
So there's actually very little actual chemistry as we understand it in this method. It's entirely the physics of the method that are
Mm,
important. Okay, so it's completely different. So what it's doing is it's firing a high energy beam at the sample, and the sample is large. It can be 500 grams. Okay,
mm,
probably that they're using. So it this beam energy is it's a high energy X-ray beam of it's about 8 or 9 MeV, and they use a linear accelerator to produce it. Now, these linear accelerators are common items at airports, for example, because they use it to look through baggage, for example. So when they say the X-ray bag, X-raying the bags, that's what they're using, a linear accelerator that's producing this high energy beam that allows you to see through your suitcase. And in this case, what it does is it irradiates the gold atoms in the sample. Irradiation is probably the wrong term. What it does, it moves the gold atom into a higher state. Okay. So it's not like neutron activation where you're firing neutrons and you change gold 197 to a radioactive gold 198 and it
mm,
decays, right? So it differs from neutron activation in that sense. This higher energy gold atom is called an isomer. So it's at a higher energy. And what it does, it decays away and goes down to its ground state. And in doing so, it emits a gamma ray. And that gamma ray is then measured by high purity germanium detector. So same type of detector that you use for neutron activation. So these are lots of them around. It's a well-known technology. The only thing about the process is that the decay time is 7 seconds, roughly 7 seconds. And that's a very short period of time. So you've got to irradiate your sample, and it's the individual atoms in the sample that are irradiated. So it's independent of matrix. That's important to know because matrix is a big problem in analytical
yeah.
geochemistry. Certainly in fire assay, it's a problem. But here in photon assay, it's the actual gold atoms that are irradiated. And then you have to move it along quickly to the detector and start measuring that gamma ray signal as the gold atoms fall back into their ground state and emitting this gamma ray. So the physics of the process are very different to anything else. It's closest to neutron activation. In neutron activation, you have to take your sample to a reactor where you have a high neutron flux, irradiates the sample. Then you have to wait 7 days for it to cool off because all the other elements also get excited and they need to decay away before you can actually measure the gold signal. So normally wait 7 days, and that's why it really didn't take off. The other process that may be similar is we using something like an XRF machine, okay? Standard XRF, except it has a high energy tube and it uses a very large irradiation tube firing X-rays at the sample. And that excites the K lines, the K X-ray lines. Whereas in EDXRF, you only have enough energy to excite L lines, which have a lot of interferences. So you can't really measure gold with handheld XRF unless you have it purified. And that's the basis of the PPD gold method. But Anglo American developed this X-ray machine where they could measure high levels of gold, but the detection limits are not great. They're of the order of 200, 300 ppb. So it only works where you've got rich gold mines and you've got high levels of gold that you want to measure. Just to differentiate the physics of these three processes, one is X-ray excitation in an XRF type machine. The other is neutron activation versus photon assay. And one of the issues that we've always had in finding a technique for gold is that it's because at very low levels. And the people who have developed photon assay have developed a technology that is able to measure very low levels of gold. But really the detection limits are around 20 to 30 parts per billion. So it's not as sensitive as far as the fire assay process. So that's really one of the issues. It's good. It's really good technique for mines where you have significant amount of gold. But essentially with detection limits, let's say your detection limit is, let's say 20 ppb, you're not really looking at quantitative data until 10 times detection limit. So really it's 200 ppb before you have confidence in your data. And that's just the statistics of detection limit measurements. Okay. So you need to be conscious of that. As I said, the photon assay works really well in mines where they have a coarse gold problem, nuggety gold, where fire assay could not really give you a good assay. And these nuggety mines generally have higher levels of gold. So the photon assay method, because of its larger sample and irradiation of the individual gold atoms in the sample, gives you a very good assay when you have coarse gold. Besides, it also is very fast. So within 10 minutes, you probably have a result. And it's only 2 minutes for the radiation measurement part of it. So it's very rapid. And last but not least is you avoid using lead, because lead is a big problem in the fire assay lab. You have to have proper safety protocols to handle it because it's a toxic chemical. And then once you've done the fire assay, you have to get rid of all the slag, which is contaminated with lead, plus all the lead buttons, etc. So you've got a big environmental problem associated with standard fire assay labs, which photon assay avoids.
That's interesting too.
So
I didn't really consider that it's just like the lead was always there and I just took for granted that you just kept on using it, but it makes much more sense that it's an environmental problem as well.
you can only use it once because now it's contaminated.
Exactly.
So you have to send it back to a refinery where they refine it. And one of the issues we have is when we choose lead fluxes is the purity of those fluxes. You're always going to get a little bit of gold in there. And if you're trying to go to lower and lower levels of gold, eventually you reach a point where you can go much lower. So essentially the detection limit is 1 ppb for the lead fire assay method when you use ICP-MS as your finish, or if you use an axial ICP. Flux definitely is one of the issues that limits the lower detection limit for gold by the fire assay method.
Interesting. So, the nuance, I love it. I guess my next question then would just be how are these assay labs and I guess suppliers as well adapting or potentially not adapting to these newer assay technologies? And are there any changes that we might expect in, say, the business models of commercial labs?
Yeah, it's interesting now. Photon assay system was developed by Cyro in Australia. So it took them 15 years of work, starting in the early 2000s. The first commercial unit was introduced in 2018. But they came out with a very different business model. These photon assay systems are very expensive to produce. So they're $2 to $4 million to put together because you need a lot of lead shielding to safeguard people from the radiation process.
Mm.
And they lease the equipment to the lab and they get a monthly fee. So they assume that a certain volume of samples. So if you don't meet that volume of samples, you can be losing money on that. Okay. So that's really the issue that certainly the commercial labs will be facing because, as I say, for every $100 of revenue that they got with the fire assay process, they now and the costs are roughly the same between photon assay and fire assay. That maybe part of that actually goes back as part of the lease fee to Chrysos, we on the photon assay technology. So they might only be getting, for the same numbers of samples, they might only be getting $80 of revenue versus $100 with fire assay. So
And you
I
don't have
think that
the buttons.
so that lower revenue for the commercial labs will certainly change the business of commercial labs. When you consider also that probably 60% of their business is gold determination. That's always the core of their business. And so if you are getting slightly lower revenue your MSA labs. So what you're seeing in North America is a proliferation of labs and new labs groups coming into the arena. One is MSA Labs and the other is Britannia Mining Solutions. So Britannia's 10 systems, 10 labs that they're going to open in North America. Essentially, we see a lot more competition, a lot more labs around there competing with the traditional labs. So and introducing a disruptive technology that is giving you results faster and probably better than with standard fire assay for high level gold samples.
Oh, so what you're saying is that whereas an ALS might rent one photon assay and be like, oh, this isn't really working out for us, we're losing money on it. But you have these new, say, Britannia coming in being like, we're only going to do photon assay. And that just being disruptor because it's faster and that's more appealing to companies in
Yeah.
general.
So what we've seen in North America is we have MSA and Britannia have introduced photon assay, and ALS is the only company among the traditional assay labs that has two systems in their Thunder Bay lab. At the moment, there's quite an interesting dynamic, I think, developing. SGS has gone in with the technology, but so far the systems are mainly at mine sites in places like Kalgoorlie and mainly in Australia.
Mhm.
A few in Africa. So we look at the photon assay technology. Certainly, there's a lot in North America. They have 35 systems out there, and they're contracted to produce about 58 systems. Most of those North America, East and West Africa, and Australia. Nothing in Latin America at the moment, but their target market is the 600 or 500 labs that are on mine sites. Okay, that's where they see the biggest impact of photon assay technology. And I think the reason it's really taken off in places like Africa, it's a lot simpler to operate than fire assay. You get, it's easier to train the people. You get a system that's put in by photon assay, and essentially they have all the software and everything already set up. And so it's a lot simpler to run photon assay to mindset. And we've seen that in that Barrick Gold signed up with MSA Labs to introduce photon assay at all of their mine sites. They're putting them in Nevada. And just a couple of months ago, Newmont also signed up with a master services agreement with Chrysos to introduce photon assay at their mine site. So the first one is going into their Ghanaian mine. So we're seeing the gradual spread of these with the big companies certainly wanting to take advantage of this new technology. And the important point for a company like Barrick is because now they have a reliable and a very fast method of gold analysis, they can measure everything. Okay, so multiple analyses of what's going into the stockpile, of what's going on in the process. And by measuring everything in the processing of gold, of the ore, they're able to improve it. So the gold yields will go up, but the costs also will come down. Okay, so I think Mark Bristow said that explicitly, that they're looking at these types of technology to improve their process. So overall, the profitability of the mining operation improves because you have a lot more measurement points, which are done very quickly. Because traditionally, they would take these samples, send them off to the lab, and the results come out and everything has been mined. So they don't mean anything except as a retrospective to what went on. But now you have the possibility of actually a control as you're mining. And in geometallurgical
Oh, that's very cool.
processes, that is really important. It's the ability to measure every step on the way provides much better control of your process. So I see that photon assay just bringing kind of revolution to mining operations, particularly when you've got complex ores and you have the multiple stockpiles, or like Nevada gold mines in Nevada, they've got multiple mines and they're moving material around within the mine. They've got different zones that they're mining. So it sometimes if you go to Goldstrike, you see all these big stockpiles there. I think managing that is going to be improved significantly with the introduction of photon assay.
So photon assay is strictly giving you gold. So there's no other elements that you're going to see from it.
It can measure silver and copper at this
Okay.
stage. you can add those in. And there are development plans to measure a bunch of other elements. Looking at the list that they have currently, I'm not sure why you'd want to measure them, but it's fairly limited in the suite of elements that can measure. There are other technologies out there that you could use, and we can talk about them because so far, I just want to differentiate the techniques. We've talked about fire assay, photon assay, neutron activation, and XRF methods. They're all, you're measuring the total gold in the sample, right? There are other methods that use aqua regia, that use cyanide, but they're only partial extractions. They're not measuring the total amount of gold in the sample. And people are using these other techniques because at a mine site, you don't necessarily extract the entire amount of gold from the sample.
Yeah.
So these other methods give you a measure of the extractable gold.
That's a good point. Do you want to just elaborate on that just a little bit for our listeners? I get what you're saying, and I love it. But yeah.
We'll move on to the other methods that have come on and out recently. So aqua regia gold has always been around. So essentially you're using acid to dissolve the sample and extract the gold. But where the gold is encapsulated, like in quartz, aqua regia does not attack silicate. So it's not going to extract that gold. So usually aqua regia is 95 to 98% of the gold is extracted. And we always understood that. And therefore, in most cases, we used aqua regia in soils where you don't have encapsulated gold and you have most of the gold adhering to soil particles. So aqua regia was used in soil geochemistry. The advantage of aqua regia extraction, and you can also use a pre-concentration step using DIBK. You add this material there and it takes out the gold out of the aqua regia solution. So it concentrates it and you can have very low detection limits. So detection limits of 1 ppb or lower are very possible with the aqua regia methods. Okay. The other method that has been used quite a lot is cyanide extraction. So cyanide in aqua regia, you're actually dissolving soil particles or rock particles, except for the silicates. With cyanide, you're just extracting, you're leaching the gold out. So all the gold that you're going to extract needs to be open to the cyanide solution. Okay. So if it's encapsulated in, say, quartz, you're not going to be able to extract that gold. So again, extractions may be 95 to 98%, but still it's used in a lot of labs because that's the amount of gold you actually extract from the ore. So we have this process, a very rapid process called leach, which does the extraction in 1 hour. And it's amazing. Works. It just has some accelerants built into it, and you can mix the tablets with the sample and add water, shake it up. So it's a very simple method. Okay, don't need a lot of other analytical technology. You then take the cyanide and run it on an AA, and you have your gold. So within a couple of hours, you can measure quite a lot of samples. And they have expanded this with a process known as PAL. So they have about 50 crucibles in the system, and they have put the sample in, coarsely crushed sample, and they pulverize it as they leach it. And again, within 1 hour, you can take them off and start to measure them. So the capital cost of PAL system is very low compared to other systems out there. Excuse me. The other new technology is something called cold block, which was developed here in Canada. It's come around recently. And what it does, it uses an infrared heater on the sample. So using aqua regia, and you use an infrared heater, and that accelerates the reaction. So within minutes, within 10 minutes, the reaction is done. You can take the sample off and measure it. So it's a very fast way of getting very good gold assays. And the Amara project on it showed that the recoveries were really excellent. They were 98 to 100%. That's a new method that's come along, and it's used at a couple of mine sites, one in Canada, one in Australia. The new gold mine out west is using this method because they have a lot of copper in there that interferes with the collection of gold by fire assay. So they're using cold block technology as part of their assay process, and they're able to measure copper as well at the same time within the sample. The other method that is also fairly recent is called Detector. It's by PPD Gold. And it's really an intriguing process. It was developed by Mel Linton at Cyro. And essentially, what it does, it takes 100 to 500 grams of the sample, can be done in the field. So you take your soil sample, put it in a bag, add the solution, which they don't tell you what's composed of, and say it's safe, and you can carry it on aircraft, so it's not cyanide. But they add this leaching solution and mix it with the sample for about 8 hours. And they also put a device in there known as a collection device. And I assume it's some type of ion exchange mechanism, which absorbs the gold as you're mixing it. So as the gold is liberated by the lixiviant, it's absorbed by this collection device. At the end, you take that collection device out, you dry it, and then you measure the gold on it with EDXRF. And you can measure it with EDXRF because all the interfering elements that like zinc, bismuth, and other that interfere with standard gold analysis with EDXRF, they've been removed. You're able to use a fairly cheap device to measure the gold out in the field. And it's been used in quite a number of soil surveys recently because it's very much faster in getting results from a soil survey than sending the samples to a lab, which might take 2-3 months to get results. Whereas here, with this PPB gold process, detector process, you have results within a day. So if you go to their website, just examples of companies that have used this for very rapid reconnaissance type surveys in areas. The only issue that the detection limit is pretty good. It's 20 ppb, but essentially when you are doing a soil survey, you want detection limits to be much lower because you really want to get a handle on the background. So you'd ideally like them to be 1 ppb or lower in terms of detection limits. And so it's quite intriguing to see a brand new method just come out from ALS, which is called Nano Gold 51, which is using aqua regia, plus they add HF to the mix. So what the HF does, like fluoric acid does, it dissolves the silicate. So you're able to get almost total gold extraction from a sample using, I believe, 10-gram samples. But what is interesting is the detection limit is now 20 ppt. Okay.
Whoa.
Incredibly low detection limits. In a lot of situations, when you're away from the ore system, you want to get a handle of how much gold might have gone through that system. So these very low gold values around 1 ppb, you have pretty good data, are instructive in trying to map out a gold system geochemically. So it's quite interesting to see this brand new method, and it'd be interesting to see what its applications are. The issue, my concern that I have with it is that if your sample is crushed and pulverized in a standard lab, there's always the issue of contamination. It's contamination because, you're going to have the dust, and a lot of the ALS labs have extremely good dust control systems and they manage this problem. But nevertheless, the issue of contamination is one that you would definitely have to be concerned about. Certainly, when I was with SGS and we were doing MMI analysis where the detection limit was maybe 0.1 or 0.01 ppb, the sample was only opened in the weigh room, scooped out and weighed, and that was it. So it's not exposed to the lab environment. You had the solution added to it there. So you're able to control the contamination level. So at these very low levels, the issue of contamination certainly becomes important when you're using this new ALS method.
Yeah, for sure. That's just such an incredibly low number.
Yeah.
You can't even fathom it. Yeah.
So essentially on these extraction methods, 3 types: aqua regia, cyanide, and this lixiviant that Detector are using, okay? Plus the ALS variant with it, which adds aqua regia plus HF for the extraction. So that's the other technologies that are out there. In terms of capital cost, the low-cost solutions. When you're picking a method, and if cost is important, certainly in the mine site, it's expensive to build a fire assay lab. It's expensive to have a photon assay system on there. And it's a lot cheaper to have some of these other systems. So if your capital cost is a concern, you might go with the cyanide extraction leach well type method. And it is used at quite a number of mines around the world these days.
Oh, so much information. I didn't even know. I love that. I guess I'm just I think my final question here is just hearing your opinion on the future of quantifying gold concentration. We have all these automated, non-destructive technologies on the rise. Do you see any of these as a future of gold assaying? Will fire assay ever be obsolete, or will it always retain a specialized role?
I think fire assay is always going to be there as the benchmark method because we've had long history with it. One thing I didn't mention with photon assay is that you can't analyze certain types of rocks that have uranium or thorium in them, which
Oh,
causes
that makes sense.
interference. You're going to have to find another method. And the method probably would be fire assay, I think. So where you've got interfering elements, you might have to use another technique. Certainly, a fire assay would be maybe the choice there. I think we're always going to see new methods come out there. And looking at the advances in physics that we have these days, it's just tremendous development, all types of technology. We could see, I was reading the other day about a gamma ray laser system. We could see something like that developed as a gold measuring technique. So new physics is going to come out of left field and provide us with new methods. So that's the history of analytical science. I can't say where it's going to come from because I'm not up on the physics of these methods, but for sure, people are going to be looking at better ways of analyzing the gold and faster ways and cheaper ways of analyzing for gold because it's such a big part of the minerals business. It's certainly when you look at the amount of money that goes into exploration, probably 60-70% of the money raised is just for gold.
I know that stat, and I just find it so crazy. In the times that we are in, and the focus still being so heavily on gold, it's great. And when I look at my own clients and everything, I thought that I worked with a lot more diversified a portfolio, but right now it's hugely gold, and it's just wild.
Yeah, that's the truth of the analytical business. As I said, it's a huge amount of their business. It's a central part of their business. And even though we are interested in all kinds of critical metals like the
Yeah.
rare earths and lithium and whatever, each of which has their own analytical challenges, but everything is all the focus is gold, essentially.
Yeah. Are we
And
now
that's
chatizing the community? I think we should. A little bit crazy, but it's fascinating. A fascinating talk, really.
yes.
Oh my gosh. No, this has been such a great discussion and things that look, this podcast isn't necessarily for me to learn new things, but it also is. So I learned a lot. And I really want to thank you for being here, being on the show. I want to thank everybody for listening to GeoChemistea, and a big thanks to Hugh De Souza for being on the show, dishing some tea and talking about how we have been, are, and will soon be maybe quantifying gold. Thanks to our sponsor, LKI Consulting, and to It's Water and Coma Media for our music. And I'm looking forward to chatting with everybody next month.
Thank you, Sam.